Hello everyone. As a part of this lecture series on digital electronics, in today's session, we are going to discuss about D flip-flops. So D flip-flops or delay flip-flops or data flip-flops. So as generally we know what is meant by a flip-flop, it is nothing but a latch with a clock. So latch or flip-flops are 1-bit storage elements. All these things we have discussed in the previous classes. As like SR flip-flop, D flip-flop also has the same applications. It can be used in as a frequency divider in circuits. It can be used in counters. It can be used in digital clocks. It is used in shift registers, right? So all these it is used to as a basic storage element in a memory. All these are different applications of D flip-flop. So now, what is a D flip-flop? It is an electronic device that is known as delay flip-flop or data flip-flop, which is used to store a single bit of data. Here we have D flip-flop has one input and another input will be clock. Since it is a flip-flop, we need a clock. But the input is only one. When clock is high, the data is transferred to the output. When the clock is low, the output of the flip-flop is held at its previous state. This is the working principle of D flip-flop. D flip-flop is a very simple type of flip-flop. If you see a D flip-flop, it is a minimalized version of SR flip-flop. In SR flip-flop, when we see when S and R are same, it took the condition that it acts as a memory, or S is equal to 1, R is equal to 1, it will be an invalid state. If S is equal to 0 and R is equal to 0, it acts as a memory. The other two inputs are when S is equal to 0 and R is equal to 1, it has a value. When S is equal to 1 and R is equal to 0, it has another value. So, see, out of the two inputs, S and R, both are complement to each other. D flip-flop take the advantage of this and use it. This is used as a simplified version of SR flip-flop when when two conditions, that is S is equal to 0 and R is equal to 1, and its complements are being considered. And so see the circuit, this is the same circuit. These part is same as SR flip-flop, and this is an SR latch. These two NAND gates together form an SR latch. And see, this is SR flip-flop. The four NAND gates together forms an SR flip-flop. Normally, we have the S and R here as inputs for these two NAND gates. Here we see it is a D flip-flop, and so we have only one input. We don't have two different inputs. So how the inputs are being distributed to these two NAND gates? Listen here. So here D is being directly given, that is considered as 0. D is equal to 0. So if D is equal to 0 for the NAND gate 1, and see, this is an inverter or a NOT gate. So here the output of this NOT gate will be 1. So to this inverter 1 is being given. So when S is equal to 0, R will be equal to 1. That condition is satisfied. We did not take two different inputs. Instead, we give one input, and using a NOT gate, we have complemented the input, right? So now when D is equal to 1, this point will be 0. When this point is 0, this will be 1, and vice versa. So it acts like a SR flip-flop, but with a minimized version. And so see here, when there is no clock, whatever be the data, it maintains the previous state, no change. That is, it maintains the memory state. When D is equal to 0, see, the output is also 0. When D is equal to 1, the output is also 1. This is why we call as data flip-flop 2. So when D is equal to 0, reset, that is Q is equal to 0. And D is equal to 1, S is equal to 1, right? That is set. So this is the truth table. Now coming to the characteristic table, as we know, characteristic table is the one which defines the input which when we give the input and the present state, we can define the output of that flip-flop. That is what characteristic table is. So here the input is only one D input and the present state is Q1. So what will be the output? This is derived from the truth table. And now comes the excitation table. And this is the D flip-flop characteristic equation. Now if you see here this characteristic table, it has two inputs and so four different combinations. So we'll be having a 4-cell K-map. So from the 4-cell K-map, we can derive this output is equal to, next state is equal to D. We can define it from this characteristic table too. See, whenever Q next previous state, it follows D, right? Qn plus 1 is 0, D is 0. Qn plus 1 is 1, D is 1. It follows, right? So that is, so the equation is Qn plus 1 is equal to D. So SR is a simplified, D flip-flop is a simplified version of SR. So this is for your assessment. What is the primary function of D flip-flop and digital circuits? In a D flip-flop, what happens to the output when clock signal transitions from low to high? That is during the rising edge. What happens? This is for your assessment. Hope you understood. Thank you.